Hello everyone, welcome back to Calculus 1 online at Frederick Community College with Professor Lockman. In this lecture, we will discuss antiderivatives and indefinite integrals. I split up this lecture into two portions. So in the first one, we will discuss the definition and some motivational examples. And then in the second part, we will go over more involved problems. Let's start with the following definition. A function, big f of x, is an antiderivative of little f of x if the following equation is true. Big F prime is equal to little f of x for all values of x in the domain. So that is a formal definition. Let's take a look at an example that will explain this concept. Suppose we have the following function. F of x is equal to 2x. What is the antiderivative of this function? Now, we should think about it in the same way as we thought about derivative, except backwards. Okay, so now this is the derivative that we obtained once we differentiated the function big f of x. So what is one function such that when we take the derivative, we get 2x? Well, it's fairly easy to determine that. Let's say f1 of x is equal to x squared, and we can check x squared prime, that is indeed 2x. So this is one function that is an antiderivative of our linear function 2x. And here on the graph, you see the graphical connection between those two. What's happening from negative infinity to 0? Well, on this portion of the domain, our quadratic function is decreasing, and that corresponds to the derivative function being negative, right? So negative over here, and our function is decreasing. All these tangent lines will have a negative slope. All right. What happens on the other portion of the domain? So from 0 to positive infinity, so that's over here, our parabola is increasing. Okay, so over here the derivative is positive, over here it's negative. Okay, and what happens to the tangent lines? All of the tangent lines on this portion of the domain will have positive slope. Okay, so that's the graphical connection between the function and the derivative. Now, is this the only function that is the antiderivative of little f of x? No, you say, how about this one? f2, and let's say this is x squared plus 3. Okay, we can check that if we differentiate this expression, we once again get 2x because the derivative of 3 is 0, and the graph of this function would be the same as this parabola, except it's shifted 3 units up. So something like this, and you can see that the behavior is still the same as far as increasing and decreasing, right? It is still decreasing on the interval from negative infinity to 0. It is increasing on the interval from 0 to positive infinity, and it is reflected by the behavior of the derivative, which is 2x. All right. Then what other function can we find so that its derivative is 2x? How about x squared minus 1? Well, we can check that the derivative of this expression is also 2x, and the graph of this function would be that same parabola, but it's shifted 1 unit down, so it will be somewhere here. And you can see that the graphical connection is still there. That's described by what? Where our function is decreasing, that is where the derivative is negative. Where it's increasing, the derivative is positive. So now we found just two functions that whose derivatives produce 2x. And you might say, well, wouldn't it work for any constant? And the answer is yes. So what we can write is the following. We have a family of antiderivatives, infinitely many of them, and it's defined by x squared plus c, where c represents a constant. So this is an arbitrary constant. Okay, so when we take the antiderivative, we don't really know what that constant is, so we're just going to put a letter that represents a constant. So that means there are infinitely many of such functions, so you can think about all these parabolas going up and down, shifted up and down, and whose derivative will be the same function, 2x. Okay, so now let's talk about these two operations, differentiation and integration. So differentiation is something we just discussed in our class. We've mastered our skills of computing derivatives and solving application problems. And what did we do? So let's say we take a function and we apply an operator of differentiation. So our function here is an input. Okay, take some function. Think about it as you put it in a box, you do something to it, you differentiate it. What comes out, your output, is the derivative, little f of x, and it is one unique function. There's only one output that we can get here. Now, the reverse operation is integration, okay, where the input is one function, okay, and the output is a whole family of functions. Output is infinitely many, unless we have initial conditions, and that is something that we will discuss in this class. But if we don't have initial conditions, then we don't know what that constant is, so we get infinitely many functions. That is the answer for the antiderivative. Okay, so that's one way to think about these two operations. And now we're ready to discuss the notation for the integral. Okay, so let's discuss this notation here. This symbol, kind of like a long S, this is the integral symbol. Okay, and then it says integrate our function, little f of x. This is what we're going to refer as integrand. And then dx, that tells us the variable of integration. Okay, so this is saying integrate f of x with respect to x. So this is variable of integration. And once we compute that quantity, okay, that function, whatever this function is, this is the antiderivative. And we also have our arbitrary constant. Okay, so this is our constant right here. So these are the components of integration. And what we're going to do for the rest of the class, we're going to master this concept of undoing derivatives. And we're going to talk about very, very basic integrals at first, and then we'll get more into involved problems. And if you are continuing your study of calculus and going to the second portion of the class, Calculus 2, your main focus will be on methods of integration. Okay? So now let's go ahead and take a look at just some very basic examples. Okay, so let's say we have the following setup. It says integral of the function x cubed minus 2x plus 1 dx. We would like to compute or determine the antiderivative of this function right here. So my integrand in this case is this expression, x cubed minus 2x plus 1. Okay, so what do we do? Well, I need to think about it. what would I need to do to undo the process of differentiation? And let me remind you, when we were working with polynomials, we were decreasing exponents by 1, right? So if I start with x cubed, well, now I'm undoing this process. That means what? I'm going to increase my power by 1. But notice that my coefficient in front of x cubed is just 1. If I were to differentiate x to the 4th power, I would have 4x cubed. I don't have a 4 right here. That means I need to divide by 4 in order for me to get x cubed in the process of differentiation. So again, think about it as we're undoing the process of differentiation. All right, and we're going to check it. We're going to check our answer. What about negative 2x? Well, this would be just x squared, right? Okay, and then what about 1? That would be x, and we don't forget about the constant c. Okay, so now, since we're just learning about this concept, it's not a bad idea to just check. So let's take our expression, and we're going to differentiate it to make sure that we do get the integrand. Okay, so this is d dx of this polynomial of 4th degree. So if we apply all the rules that we know, what do we get? Plus 1, plus 0, and 4 and 4 cancels out here. So we get x cubed minus 2x plus 1. And that is indeed what we started with. Okay, so the answer for this first problem is 1/4 x to the 4th minus x squared plus x plus c. And it will take you some time to get used to writing that plus c. Okay, but it is important to not forget it, okay, for integrals that are indefinite. Okay. All right, let's take a look at the next example. All right, here I have the integral of the following expression, square root of x minus sine of x dx. I'm going to go ahead and rewrite this term as x raised to 1/2. Okay, so what is my answer here? Let's deal with one term at a time. So x raised to 1/2. 1/2 plus 1, that's going to be 3/2. I'm adding 1 because I know that is how we apply the power rule, by subtracting 1. So to undo it, I'm going to add 1. So x raised to the power 3/2. And I'm looking at my expression over here. The coefficient here is 1. And if I were to just differentiate x raised to the power 3/2, I would get 3/2 as the coefficient. What does that mean? That means I need to divide by that or multiply by the reciprocal. So 2/3 comes here. So 2/3 times x to the power 3/2. And then now I need to undo the derivative of a trig function, and I have negative sine of x. Well, is there a function whose derivative is negative sine of x? And the answer is yes, it's just cosine, right? So plus cosine x and then plus c. Okay, so let's go ahead and check this. If I were to differentiate this expression, if you can do that in your head, that's great. You don't need to do that, but I think it's not a bad idea to just check. What do we get? So this is 2/3 times 3/2 x to the power 3/2 minus 1. The derivative of cosine is negative sine. The derivative of c is 0. And what do we get? So this is x to 1/2, or square root of x, minus sine of x, and that is exactly what we started with. Okay, so the answer is here. This checks out. All right. Okay, let's do one more example that's fairly straightforward. we have an integral of e to the 4x minus 5. Okay, so we know how to differentiate exponential functions with base e. Okay, let's see. If I were to just differentiate e to the 4x, I would get 4 times e to the 4x. I don't have 4 here. I have just 1. So that means we need to divide by 4. And what about the constant term, negative 5? Okay, well, that's just negative 5x and then plus c. And I'm going to go ahead and check. So let's take the derivative of the expression we just got. All right, so what would that be? So that's 1/4 times 4 e to the power of 4x minus 5 plus 0. So that is our integrand. That checks out. So that is our answer for this example. Okay, so if this is the first time you're seeing antiderivatives and integrals, take your time thinking through these problems. You will see that if you know your derivatives very, very well, this process will be intuitive. So now I'm going to show you the table of differentiation formulas and their corresponding indefinite integrals formulas. I will be posting this on our course site, and of course it is also in the textbook, and you can see the connection here. I'm not going to go through the whole thing, but you can have that on your formula sheet. This is just to remind you very basic differentiation formulas. This is what we know. Okay, so we know this. Okay, so the derivative of a constant is 0. Then we have the power rule, derivative of natural log, exponential, trig functions, and inverse trig. Okay, all of that. And then on the right side of this table, we have indefinite integrals, or the reverse process. So now when we see integrands, we need to recognize that they might be derivatives of some function. So for example, when we see integral of secant squared of x, we need to recognize that the antiderivative is tangent. Okay, and some expressions over here where we're working with inverse trig functions. All right, so we're going to go ahead and stop right here. Again, what we're going to do for the rest of the class, we're going to focus on integration. Okay, so this is what we're learning. We are learning this. Okay, and again, you will notice that if you know your derivatives rules very, very well, this process will be somewhat intuitive and easy. Okay, so that's what we're going to do for the rest of the class. I'm going to stop this portion right here, and in the next part of this video, we will go over problems that you will encounter on your homework.